Hello ladies and gentlemen, hope everyone is doing well today. So this video is going to go over a couple more examples similar to what we saw on Friday when we introduced section 7.1. Particularly, we're going to take a look to see how we can verify if a given function y is a solution to a particular differential equation. Now, it may not always be the case, but we just want to ensure that we're following the correct techniques when taking the derivative and then plugging them back into our expression to see if we get a true statement. So it'll give us a nice little refresher on some techniques that we learned back in chapter 3. And this one in particular is going to remind us of chain rule. Because here we have 4 cosine of 2x plus 6 sine of 2x because we have an outside function and then a function within that particular function. So for this one we do use the chain rule. We still have that 4 in front. Now derivative of cosine is just going to be a negative sine. And because we are using the chain rule, that means we also have to take the derivative of this inside function and multiply it to the outside. So derivative of 2x just becomes 2. Similar with the second term here, we're still going to have a plus 6. And then derivative of sine is cosine 2x. And we take the inside function there for its derivative, and that's also going to be 2. So if we simplify that out, we get a negative 4 times 2. That's going to give us a negative 8 sine of 2x plus 6 times 2 is going to give us 12 cosine of 2x. Now, unfortunately, this is just the first derivative. In this case here, we actually have to take the second derivative, and that's evident by the 2 apostrophe marks that we see over there. Another fun fact, this type of differential equation is also what's known as a second order differential equation, and the order just relates to the highest derivative that you have in your particular expression. So when we find the second derivative, we're just going to take the derivative of that new function that we found, and it's going to be the same sort of process as we saw earlier. So we're going to use chain rule again. Derivative of sine is cosine. Then we multiply by the 2. And then over here we're going to have plus 12 times the negative sine of 2x. And then we're going to multiply that by 2. And so if we clean this up, we get negative 8 times 2. That's going to give us a negative 16 cosine of 2x, and then minus 24 when we do 12 times 2 times sine of 2x. Okay, so we got pretty much the hard steps out of the way, and now all that we have to do is just plug them back into this equation over here. So we know that our second derivative is going to become our first term, so we can just rewrite that expression that we found a couple of seconds ago. That's going to be minus 24 sine of 2x. And then we also have to plug in our original equation for y, so we're going to have plus 4 times 4 cosine of 2x plus 6 sine of 2x. And we want to see if that is going to simplify to be equal to 0, as we see over here. So we can distribute that 4 across. So our first two terms are still going to remain the same. And when you do 4 times 4 over here, we're going to get 16. So we get a plus 16 cosine of 2x. And then we also get a plus 24 when we distribute to that 6 over here. And that's also going to be sine of 2x. Now, if you want, you could rearrange these terms. But if you notice how we do have the same expressions, except one's going to be a positive, one's going to be a negative for the cosine. So those are going to cancel out. And the same situation appears when we have a negative 24 sine of 2x and a positive 24 sine of 2x. So those are all going to cancel out, leaving you with 0 is equal to 0. And so we just verified that this function is indeed a solution to this particular differential equation. Okay. Now the other type of example that you may see is an expression in which both x and y are on the same side of your equation for that particular function. So in case they ever mention the letter c, you always want to think of c as being a real number. So in other words, it's just a constant. It could be like -1, it could be pi, or it could be the square root of, say, 127. And what we want to do is just verify that this particular function now is a solution to this differential equation. Now, as you may have noticed, when we've been deriving these functions here, we've always been doing it with respect to x. And that statement is still going to be true with this particular example here, except now we're going to go back to a technique of implicit differentiation. And that was something that we saw in chapter 3. And there's really only one extra step when it comes to these types of examples. I'll put a little star right there to help us indicate. Okay, so, whoops. So we still take the derivative of this first term as we do normally, so that's just going to be 10x. Now, keep in mind that whenever you deal with terms involving y, implicit differentiation still has us take the derivative as we would normally, so we just multiply the 3 to the 12, we get 36y squared. But because you took it with respect to x, you also have to include a dy over dx in there, and that's still going to be equal to, or actually not still, you take the derivative of a constant, you're just going to get 0. So implicit differentiation enables you to take the derivative on both sides. Now, to make this a little bit nicer too, remember that there are multiple representations for a derivative, so dy over dx can also be written as y prime. So that way we're kind of in tune with the notation that we have here for our particular differential equation. Now, notice how these two terms here, right, they're just half of what these two terms were when we did our implicit differentiation. So if we divide everything by 2, right, this in turn is still going to give us 5x plus 18 y squared y prime, and anything that you divide into 0 is still going to be 0. So this, in fact, is actually a solution to this particular differential equation. So sometimes you may want to just divide by a particular number on all sides, so that way it exactly matches this equation over here. Okay, now to kind of give you a sneak peek too as to how we actually come up with these solutions, these are going to be some examples that we're going to see more of in section 7.3. And the key is really just to get all the variables on one side of the equation each. So you're going to have your y's over on one side and then your x's on the other side. And we're just going to figure out how we can figure out a general solution. So what we can do, because the nice thing about your differential equation, it's expressed as kind of like a rate. You can just multiply both sides by dx. That way they cancel out over here. You get dy is equal to 3x squared dx. Now, because we're trying to find a general solution, we want to get rid of these derivatives. And as we recall from chapter 6, the inverse of taking the derivative is taking the integral. So we're just going to integrate both sides with their respective variables individually. And so when you have, say, the integral of dy, it's also the same as the integral of 1 times dy. And so if you integrate 1, you're just going to get y back. Okay? And then over here, we're still taking the integral in relation to x, so we're going to add 1 to that power of 2, so that's going to be a 3x to the third, and then we just take that new exponent and divide it into 3. And we're also going to add the plus c because, again, this is an indefinite integral that we deal with here. And we can clean this up a bit, so we find that the general solution is going to be x to the third plus c. And the cool thing about differential equations too is that the general solution that you find is actually an infinite number of solutions, and that's evident with the plus c over here because you can add any sort of constant that you want to x to the third. If you were to take the derivative, you would still end up getting 3x squared back as a result. So your homework for tonight is still going to be the worksheet for 7.1. And then tomorrow we're going to take a look at more of a visual approach behind these differential equations in illustrations known as slope fields. And with that, I hope you guys have a great rest of the day.